Welcome everyone, and this lecture is wave motion lecture number 4, and we are dealing with longitudinal waves. We have already started with longitudinal wave. We have seen what longitudinal waves are. In longitudinal waves, what happens is if the wave is propagating in the x-axis, particles are also oscillating in the same axis. This propagates by the phenomena of compression and rarefaction. At some position, the particles are very close to each other. The pressure is very high. The density is very high. That point is known as compression. And the points where pressure is low, particles are away from each other, is known as rarefaction. Distance between two consecutive compressions or two consecutive rarefaction is known as wavelength. We have also seen the equation for a longitudinal wave, and we write that equation in this form: delta P is equal to delta P naught into sine of omega into t minus x by v. It is exactly in the same form as we had written for a transverse wave. The only thing is, in transverse wave, we have written it like this: y is equal to a sine omega t minus x by v. Here y was the displacement from the mean position. Here delta p is the difference from the atmospheric pressure if we talk about sound waves. A was the amplitude maximum displacement. Here delta P naught is the maximum difference in pressure. Remember, if there is a negative sign, this wave is traveling along positive x. If there is a positive sign, then the wave is traveling along negative x. Do we remember this? Do we understand this? Great. We have already seen that. So let us now move ahead and see the other aspects of sound waves. Basically, longitudinal waves. In longitudinal waves, the only thing that we are going to understand or study about is the sound wave, and that is the most important aspect over here. So we will see some more points about sound waves, and the heading for today's chapter, the topic is characteristics of sound, and we will be dealing with three characteristics of sound. You must have heard about these three characteristics. The first one is known as loudness, the second one is known as pitch, and the third one is known as quality. We will go through these three characteristics. They are coming to your screen now. These characteristics of sound. You can call them characteristics of musical sound as well: loudness, pitch, and quality. Loudness, again, we always use the term loudness. Sir is very loud. Class is very loud. Sir, please speak loudly. So what do you mean by loudness? Loudness is a very subjective term and is related to the intensity of sound. What do you mean by intensity? Is the amount of sound passing per unit time, per unit area, and it is measured in watt per meter square. So basically, loudness relates to intensity. How much energy of sound per unit area, per unit time are you receiving? That is known as the loudness of sound. Do we understand this? Yes or no? Loudness relates to the intensity of sound, and that is what you must remember. And intensity is the amount or the energy of sound passing per unit area, per unit time. The energy is, the unit is watt, joule per second per meter square. Do we understand this? Okay, I'll give you a minute to note it down. Well, we have seen what do we understand by loudness. We must also understand the SI unit of loudness. And I'm sure you have heard about this unit. It is known as bell or decibel. You must have heard about decibel. Yes or no? You might have heard about decibel. This is the commonly used unit, but the SI unit is actually bell, and this decibel is actually 1 by 10th of bell. Do we understand this? Yes or no? The decibel is the unit that we normally use for sound. Now, how do we understand the unit of sound? It is defined by using the concept of zero level or threshold of hearing. Now, you must be aware of this threshold of hearing. What do you mean by this threshold of hearing? Is the lowest intensity of sound that can be heard by the human ear is known as the threshold of hearing. This threshold of hearing is denoted by the letter I naught. The threshold of frequency, if the frequency of sound is 1 kilohertz, this is the lowest intensity that can be heard by human ear, that is 10 raised to the power minus 12 watt per meter square. Do we understand this? Now, if you understand that this is the lowest intensity of sound that can be heard, and this is written as I naught, then this equation gives me the loudness of sound in bells. L, loudness of sound, is log to the base 10 I by I naught. I naught represents the threshold of hearing. If the intensity that we are hearing is 10 times of I naught, 10 times of the minimum value that can be heard, then loudness will be log to the base 10, 10 I naught divided by I naught. 10 se 10 will get cancelled. Log of 1, log of 10 to the base 10 will be 1. So the intensity will be 1 bell. So when we say that the intensity of the sound is 1 bell, it is the intensity which is 10 times the threshold of hearing. Do we understand this? Well, that is how we define the intensity in bell, but the practical unit that we use is decibel. 1 decibel is 1 by 10th of bell. So in decibel, the formula becomes for loudness 10 times log to the base 10 I by I naught, where I is the intensity, minimum intensity that we can hear, and I naught is the threshold of hearing, which is 10 raised to the power minus 12 watt per meter square. I will give you 2 minutes to note this down. I hope we are clear with this. Yes or no? Give you 2 minutes to note this down. Okay. Now let us see some factors on which loudness or intensity of the sound depends on. The first factor is the amplitude. I've already told you that intensity is proportional to amplitude square. Yes or no? Then it is about area. Intensity is inversely proportional to area. That means it is energy per unit area. So if the area is less, intensity will be more. If the area is more, intensity will be less. Distance, intensity is actually inversely proportional to distance square. So as you go away from the source of sound, the intensity will decrease. It also depends on the density of the medium in which the sound travels. It is directly proportional to density. I had given you the formula for intensity as well. It depends on the presence of other bodies, and it also depends on the motion of the medium. So these are the 6 points. Out of this, you must remember these 4 points which are very important. Intensity is proportional to A square. Intensity is inversely proportional to area. Intensity is inversely proportional to distance square. And intensity is directly proportional to the density of the medium. Do we understand this? I'll give you a minute. Okay, then the next quality that the next characteristic that we'll have to see is pitch. Now, we somehow confuse pitch, but remember, uh, we can, with the use of pitch, we can distinguish between a shrill and a grave note. A shriller note is a note of higher pitch and it has a higher frequency. A grave sound is of low pitch and low frequency. That means pitch of a sound is something that depends on frequency. So when I say a high pitch note, it is a note of high frequency. When I say a low pitch note, it's a note of low frequency. But remember that pitch is not the frequency, but it changes with frequency. So pitch of a sound is definitely not its frequency, but it depends on the frequency. Do we understand this? Child of a voice of a child is always shriller than that of a boy and much shriller than that of a man. In other words, pitch, the pitch at which your my son speaks is very large compared to me, and it's very large compared to my father-in-law. That is how you can understand this. The roaring of a lion is of low pitch, but the buzzing of a mosquito is of higher pitch. Do we understand this? This is how you can understand which is a shriller voice. The buzzing of mosquito is shriller, whereas the roaring of a lion is grave. Do we understand this?
Yes, sir.
Please note it down, mark it, because questions from this have come many times better. Okay, and the next thing is definitely quality. You just have to see what is quality. If you see, or if you not see, if you hear sound of the same frequency and same intensity from two different musical instruments, say a sitar and a tabla, or a sitar and a violin and anything, you can make out which sound is coming from which. This characteristics of sound by which we can determine or distinguish two sources which are giving us sound of same intensity and same frequency is known as its quality. Do we understand this? So just remember this. This is all what you need to understand. We'll also understand something known as overtones and harmonics. Remember, this is what you must remember. Greater the number of overtones or harmonics, more sweeter the note appears. This is why the sound of an open pipe appears more melodious than that of a closed pipe. So basically, a sweeter sound, if someone is speaking sweetly, not speaking sweetly, if a instrument is giving a sweet note, that means the number of overtones or harmonics. These are the two words that you must understand. The number of overtones or the number of harmonics is more. You might ask me what is the number of overtones or harmonics. We will get to that in a moment. Just note down this. I'll give you a minute to do it. Well, let us move ahead and move on to the next topic. And this next topic has been dealt in great details in the lecture on transverse wave, and before that in wave optics. So I'll request you to go back to this in the previous topics just for the quick revision. What is interference of sound waves? When you have two sound waves traveling in the same direction, having same frequency and nearly the same amplitude, when they superimpose, at some points we have high intensity or constructive interference, and sometimes at some places we will have low intensity or dark fringes or destructive interference. This phenomena is the phenomena of interference. Do we remember this? We had seen two waves. Y1 is A1 sine omega t and Y2 is A2 sine omega t. And we had find out that when they superimpose, how do we superimpose them? We just add them Y1 plus Y2 and the resultant amplitude is A1 square plus A2 square plus 2 times A1 A2 cos theta ka root. Do we remember this? Yes or no?
Yes, sir.
Just note it down. Well, continuing on our discussion on this interference, constructive as well as destructive. If we talk in terms of intensity, intensity is directly proportional to A square. So this becomes the formula for intensity. The next heading is constructive interference, and it happens when the angle or phase difference is 2 and pi. The value of cos theta becomes 1. The maximum amplitude becomes A1 plus A2 and the maximum intensity becomes root over I1 plus root over I2 ka whole square. I guess you remember this. Yes or no? No or yes?
Sir.
Yes, sir. Well done, sir. Then quickly cover we quickly cover the destructive interference as well. In destructive interference, the phase difference becomes 2n minus 1 pi. The minimum intensity becomes A1 minus A2. The minimum amplitude becomes A1 minus M2, A1 minus A2, and the minimum intensity becomes root over I1 minus root over I2 ka square. If the two interfering sources have the same amplitudes, then maximum intensity is 4 times and maximum amplitude is 2 times A naught. Minimum intensity in those cases becomes 0. Then we have seen the relation between path difference and phase difference. In terms of path difference, for constructive interference, path difference must be n lambda. For destructive interference, the path difference must be n plus or n minus half. Do we remember this? Yes or no? No or yes? Please note it down while I give you 2 minutes. Well, then, the next topic that we are going to discuss is reflection of sound waves. We understand sound is also a wave. We have seen the laws of reflection. Whenever sound wave will encounter a boundary between two mediums or it encounters a wall where it cannot go on the other side, it will be reflected back. The angle of incidence and the angle of reflection will be same. The incident ray, the normal ray, and the reflected ray will lie in the same plane. We have already seen those laws of reflection. What we must understand here is again when sound wave gets reflected from a rigid boundary. Now instead of rigid boundary, we can also say that it is getting reflected from a denser medium. Do you remember we had seen this reflection in transverse wave? Yes or no?
Yes, sir.
Here we are also calling it as rigid boundary. When any wave gets reflected from a denser medium or it gets reflected from a rigid boundary, the phase of the wave is reversed. That means it undergoes a phase difference of pi. Here you can see what I have underlined. The initial wave was y is equal to a sine omega t minus kx. When it reflects from a denser medium, and remember it becomes a dash. If it is not getting 100% reflected, a dash will not be same as a. If it is getting reflected 100%, a dash will be same as a. Do we understand this?
Yes, sir.
So the reflected ray becomes a dash sine omega t plus kx. Why it is plus kx now? Because now it will be moving in the negative x-axis, and you can see a pi wala sign. It undergoes a phase difference of pi. Please remember this. The new term here is rigid boundary. Rigid boundary is nothing but a denser medium. Do we understand this?
Sir.
Note down whatever I have highlighted in the text. Then we must also look at what will happen if it is getting reflected from a rarer medium. Rarer medium here is also known as free boundary. So what will happen? It will not undergo any phase change. That means a compression will be reflected as compression and a rarefaction will be reflected as a rarefaction. If the actual equation is y is equal to a sine omega t minus kx, the equation of the reflected ray will become a dash sine omega t plus kx. One is moving in the negative direction, one is moving in the positive direction. The original ray moving in the positive direction and the reflected ray moving in the negative direction. Please note whatever I have highlighted. Remember, it's a very important question, can be asked in different ways. Well then, as soon as we are done with reflection, now we will be doing superposition of two waves of equal magnitude, of equal amplitude and frequency, but traveling in the opposite direction. So two waves of equal frequency and amplitude, but traveling in the opposite direction. When they are superimposed, what happens is stationary wave. We have already seen that. Why do we call it a stationary wave? Because energy does not propagate. The wave is not progressive. Energy is not getting transferred from one place to another to other place. The wave is actually extending and contracting relative to its mean position. So the wave does not go anywhere. There is no transfer of energy, and this wave is known as stationary wave. Again, a revision of what we had done in the transverse wave wala section. I'll give you a minute to highlight the important points. I hope you have noted down the concept of stationary wave. And now we are going to see some mathematical analysis. We will be analyzing two types of cases. And I hope that you write both these cases, note them down and understand the difference between the two cases and the difference in the equation that is coming from the two cases. The first case is when the wave is get wrong color, sorry, when the wave again wrong color, when the wave is getting reflected by a free end. And the second case where I have used the pink color is when it is reflected from a rigid end. I have already told you what happens when it is reflected from the free end. As you can see over here, the original wave is sine omega t minus kx. It is getting reflected back 100%. The reflected wave is omega t plus kx. It is moving in the negative direction, but it has not undergone any phase change. But if you look at the pink side, the original wave was omega t minus kx. The returning wave, the reflected wave is minus a sine omega t plus kx. It has undergone a phase difference of pi. Do we see this? Yes or no? No or yes?
Yes, sir.
When you superimpose these two waves, what happens, bacha, is yeah. What happens, bacha, is on the left hand side you have y is equal to minus 2a cos omega t sin x sin kx. You will ask me, sir, how this has come? Beta, this is a trigonometric formula that has been used. Sin a minus sin b, because there is a negative sign here. This is sin a minus sin b ka formula. On the left hand side, if you see, it is sin a plus sin b ka formula. So the difference in the two equation is, in the yellow wala equation you have 2a के साथ sin omega t, sin में omega t है 2a sin omega t, and on the right hand side you have 2a cos omega t. Do we understand this?
Yes, sir.
That's it. So that is how you, one equation will have sin, the other equation will have cos. The difference it creates is the maximum displacement of particles from the mean position. On the left wala equation is 2 times a cos kx. On the right wala equation it is 2 times a sin kx. Sorry for the mistake. I hope you understand this. This is just a trigonometric formula put together. I'll give you a minute to note down the finer points. and understand the difference. Well then, continuing on with the previous equation that I have given you, I have given you that the amplitude in the yellow equation is 2a cos omega t, and the amplitude in the right equation is 2a sin omega t. What difference does it make is when the amplitude is maximum, that point is known as antinode. Do we understand this?
Yes, sir.
Here the antinode happens as n lambda by 2. Distance between two antinodes is always lambda by 2. But on the right hand side, we have position of antinode at lambda by 4, 3 lambda by 4, and 5 lambda by 4. Remember the distance between the two antinodes is always lambda by 2. But between left equation and the right equation, what you see is the position of antinodes. Remember, antinode is the point where amplitude is maximum. Do we remember this? Yes or no? No, yes.
Yes, sir.
Antinode is the point where the position where the amplitude is maximum. The only difference that it creates between the yellow one and the pink one is that the position of antinodes have changed. On the left hand side, the position of antinodes are 0, lambda by 2, 3, 2 lambda by 2, 3 lambda by 2, 4 lambda by 2. But on the right hand side, it is lambda by 4, 3 lambda by 4, 5 lambda by 4, and so on. I'll give you a minute to win it. We have done antinode, so we must do the opposite of antinode as well. The opposite of antinode is a node, and what is the node? Node is the position where the displacement is 0, yes or no? So, in case of the left hand side wala equation, the position of antinode becomes lambda by 4, 3 lambda by 4, 5 lambda by 4. Whereas on the right hand side, it becomes 0, lambda by 2, 2 lambda by 2. So basically what has happened is the position of node and antinode have interchanged. On the left hand side, what was the position of antinode has been taken by the position of node on the right hand side. Do we understand this? Between any two consecutive nodes, the distance is lambda by 2. Between a node and an antinode, the distance is lambda by 4. Please note this down. What we'll do now is what we have already done, but we will again go through this, and it's a comparison between progressive wave and stationary wave. So we'll understand both these waves side by side together. In progressive wave, these waves will move, advance in a medium. Energy is getting transferred from one point to other. Do we understand this? Yes or no?
Yes, sir.
But stationary waves, energy is not getting transferred. They are confined between 2 points. In case of progressive waves, what has happened here? Something wrong has happened. Okay, I've corrected it now. In case of progressive waves, all at no instant all particles of the medium pass through their mean position. It does not have an upper. All particles are performing their own SHMs. But here in stationary waves, 2 times in one cycle, 2 times in one time period, all the particles simultaneously will cross their mean position. Do we understand this? Progressive wave energy is transferred, stationary wave energy is not transferred. All particles, they are having different pressures and different intensities at different points at different times. Remember here, intensity is fixed. At node it is 0 and at antinode it is maximum. Here particles are vibrating with the same amplitude in progressive wave. In stationary wave, the amplitudes are different. Do we understand this? Please note this down while I give you 2 minutes. Let us move ahead and move to the most important part of this chapter, which is known as vibration of air column in pipe. How does air column vibrate in pipe? Now we have to do two cases. Case number one is for a closed pipe. When I say a closed pipe, as you can see, it is closed at one end and it is open at the other end. Do we see this? Yes or no? It
Yes,
is
sir.
closed at one end and open at other end. Remember, and the most important thing here is node is formed at the closed end and an anti-node is formed at the open end. Do we understand this? Do we see a N here? N standing for node and A standing for the anti-node. Yes or no? No or yes?
Yes, sir.
L is the length of the pipe. There is one node and one antinode. The distance between the node and the antinode is lambda by 4. Do we understand this? So my L becomes lambda by 4 or my lambda becomes 4L. This is the first wave that can be formed and this is known as the first harmonic or the fundamental node. Do we understand this? It only has one node and one antinode. This is known as the first harmonic or the fundamental node. Do we understand this? Are we there in the class? Here we have one node and one antinode. This is known as first harmonic. If you look at this, we have got one, two nodes and two antinodes. This is known as the third harmonic. Here the length of the pipe becomes 3 lambda by 4. In the third case, we have 1, 2, and 3 nodes and 3 antinodes. Do we understand this? Yes or no? Can I have some raised hands? Great. I'll give you a minute to draw all these diagrams. We are done with the diagram. Then we must note these things. In first figure, what we had drawn is known as the first harmonic. Its frequency is given by F1. The second figure shows you the third harmonic. Its frequency is 3 times F1. And the third figure gives you the fifth harmonic. Its frequency is 5 times F1. How do you get the value of F1? F1 is V divided by lambda. V is equal to F lambda. So F1 is V divided by lambda. Lambda in that case was 4L. So F1 becomes V by 4L. So F3 becomes 3V by 4L. Lambda 3 becomes 4 by 3L. Similarly, F5 will become 5V by 4L and lambda 5 will become 5, 4, 5 by 3L. Do we understand this? If I write the formula for F3, that will become 5V by 4L. In that case, the formula for this is F5. I've written F3. F5 will become 5V by 4L. In this case, lambda 5 will become 4 by 5L. Do we understand this? Yes or no? I'll give you a time to note this down. Well, then, there is sometimes a thing known as end correction. What happens in an end correction? The antinodes, which are there at the open end, they do not occur on the open end. They occur slightly outside. So we have to correct the end. We have to put an end correction. This end correction is 0.6 times R. where r is the radius of the pipe. So the effective length of the pipe becomes L plus E, or it becomes L plus 0.6 r. Please note down, this is the end correction for a closed pipe. A closed pipe only has one open end, and therefore we have correction only at one end. Please note this down, a very important point. Now let us move ahead and see what we call as open pipe. When I say open pipe, I mean it is open at both ends, and you can see that open pipe in your sheet right now and I'm showing it. So remember, at the open ends we always have antinode. Do we see this? Yes or no? At open end we have antinodes. This is the first overtone. This is the first harmonic. Its frequency is given by F1. Remember the fundamental note or the first harmonic here. It has a wavelength of 2L because lambda 1 by 2 becomes equal to L. Distance between two antinodes. Here it is one antinode. Here is the second antinode is lambda by 2. Lambda by 2 becomes equal to L, or lambda 1 becomes 2L. The frequency in this case is known as the fundamental frequency or the first harmonic. Do we understand this?
Sir.
This one is known as the second harmonic. This one is known as the third harmonic. Remember, in case of closed pipe, we had first harmonic, then we had third harmonic, then we have fifth harmonic. Only odd harmonics were there, even harmonics were absent. But in case of an open pipe, we have first harmonic, second harmonic, and third harmonic. Remember, F2 will be 2 times F1, F3 will be 3 times F1, F4 will be 4 times F1, and so on. For open pipes, we have all harmonics, but for closed pipe, we only have odd harmonics. Do we remember this? Can you remember this? Yes or no?
Yes, sir.
Please note it down, and then we will move on to some question and answers on this one. So here we go with some question and answer. This is question number 1 from your sheet. The ratio of velocities of sound in dry air and humid air is the velocity of sound same in dry and humid? If yes, then what is the answer? If no, then what is the answer? Where is it more? Where is it less? Yes, what is the answer of this one? Dry air to humid air, what will be the ratio of velocities? Where is the velocity more, in dry or humid? It is more in humid air, yes or no? So the answer would be A. Do we understand this? Great. That was the first question. Remember, questions always come like this. The questions are pretty simple. If we understand their meaning, we will be able to solve them correctly. Let us now come to the next question, and the next question is question number 7. The velocity of longitudinal waves in solid is given by which of the formulas? A, B, C, D. The symbols have their usual meanings. What is the answer for this one? 1, 2, 3, 4, A, B, C, D. Yes, the answer here is B, root over Young's modulus by rho or density. Do we remember this? Yes or no? No or yes? That takes us to the next question, and the next question is here. The Laplace's formula for sound wave is. Remember, there was a Newton's formula, then Laplace came and corrected it. What will be the Laplace formula, or what is the Laplace formula? Can I have your answers, please? The answer is right there on your screen. And yes, the answer is B. It is gamma P by rho. Do we understand this? Comes the next question. And the next question is a pretty straightforward one. The densities of two monatomic gases are in the ratio of 16:9. The velocity of sound in the gases having the same pressure. Pressure is same. Remember, there are two different gases. Pressure is same. Densities are in the ratio 16:9. What will be the ratio of speeds of sound or velocity of sound? And your answer is which one? 16:9. What is the ratio of speeds? Can I have your answers? And the answer is definitely 3:4. Remember, it is inversely proportional to root of intensity. If the density, root of density, if the density is more, speed is less. If the density is less, speed is more. Do we understand this? Yes or no? No, yes. Well done, bacha. Well done. These are the types of questions that come. Here is the next one in line, and I hope to get an answer from you on this one. Sound waves are propagating in a medium. The moduli of isothermal and adiabatic elasticity of the medium are ER and ES. What is the velocity of sound proportional to? Is it proportional to the isothermal elasticity, or is it proportional to the adiabatic elasticity? Which process is that? Is it isothermal or adiabatic? I told you in the class. Laplace did the correction. What is the answer here? ER stands for isothermal, ES stands for adiabatic, and remember I told you it's an adiabatic process. Remember it? Newton thought that it is isothermal and therefore the formula of Newton was incorrect. Laplace came and corrected it to isothermal, say adiabatic. He said that it is an adiabatic process and the formula became correct. Do we remember this? Yes or no? No, yes. Comes the next one, the correct graph of V square and temperature. Remember, absolute temperature, temperature in Kelvin. What is the correct graph? Can I have your answers, please? Which one do you think is the correct graph? This is question number 9. Question number 9 for you. Which is the correct graph of V square with T? What happens with temperature, bacha? V is proportional to root of T. Do you remember this? Yes or no? No or yes? So V square will be proportional to T. With temperature, V square will increase. It will be a straight line and the answer would be A. Do we understand this? Can I have some raise hand that we understand this? That is great. We are doing absolutely fabulously in this section and I'm very happy. Let us now move on to the next question and see if you can give me the answer for this one. Air pressure is doubled at constant temperature. Remember, temperature has not been changed, but the pressure has been doubled. That means PV is equal to nRT. Temperature has not been changed, volume has been changed. If the pressure is doubled at constant temperature, what is the speed of sound? It will be doubled, it will be 3 times, it will be 4 times, it will be equal to its initial value. I want an answer for this. Can I have an answer for this? And the answer is correct, equal to its initial value. Remember that beta, if the temperature does not change, the speed of sound cannot change. Well done. I'm pretty impressed with what you are doing. And that takes me to the next question. And I want an instant answer from you. At what temperature the speed of sound in air becomes double of its value at 0 degree Celsius? Waiting for your answers. 0 degree Celsius, remember, is 273 Kelvin. So you need to double the speed of sound. The temperature is 273 Kelvin. What should be the temperature where the speed of the sound is doubled? And I wait for your answers here. To double the speed of sound, we must multiply temperature by how many times? One time? No. We must multiply temperature by 4 times because velocity is proportional to root over temperature. By multiply temperature by 4 times, root of 4 will be 2. That means you will have to multiply 273 by 4 times. The answer will be 1092 Kelvin. Do we understand this? Yes or no? Velocity, again I repeat, velocity is proportional to root of absolute temperature. If I want to double the speed, the temperature must be multiplied by 4. Now, let us have the answers for this one. I hope you can give me the answer. In a stationary wave in an open pipe means it is open at both ends, bacha. What is the correct answer? You have drawn the diagram. You have seen what happens in an open pipe or a closed pipe. Can I have your answer for this one? And the answer is definitely A. In an open pipe, you will have antinodes at the end, and in between them, there must be at least one node. Do we understand this? Yes or no? No or yes? Yes or no? No or yes? Well done, bacha. Let me see if you can give me the answer for this one. These are the type of questions that you can expect in the exam. In open pipe, open at both ends, where are the nodes? Where are the nodes is what they are asking us. You have 4 options. Can tell me which is the correct one, and I wait for your answers. Where are the nodes located? Oh, where are the anti-nodes located? Sorry. Where are the anti-nodes located? We've already drawn the diagram and we know where are the anti-nodes located. Where are they located? Please let me know. In open pipes. You've drawn the diagram. You've drawn the diagram. In open pipes. In open pipes. In open pipes. And I am showing you a glimpse of what we had already seen. Open pipes. I think I've shown you the answer. Yes or no? No or yes? I've shown you the answer. No, yes, yes or no. And yes, the correct answer is B, 0, one end. Then we'll have at lambda by 2 because distance between two antinodes or two nodes has to be lambda by 2. Do we understand this? Yes or no? No or yes? Well done, bacha. Let me see if you can tell me the answer for this question. Here comes the next one in line. Question number 12. Okay, I don't think you can see the entire question. I had a doubt, so just okay. I hope you can see it now. Most of the pipe in an open organ pipe is represented by which diagram? Which diagram represents, remember, which diagram represents the vibration in open argon pipe? The only answer is C. Yes or no? Do you understand this? Do you understand this? Now remember, this is the diagram for displacement wala diagram, and this is the diagram for pressure wala diagram. Remember, if you draw the diagram for pressure, it is ulta of the diagram of displacement. In displacement, we have antinodes at the open end, but in pressure, we have nodes at the open end. Do we understand this? Yes or no? So remember, if the diagram is given like this, one diagram will be for displacement and the other diagram might be for pressure. In this case, the diagram is not given like this. I just wanted to let you know. So the diagram is not given like this. Here the diagram is given only in terms of displacement. So if it is given only in terms of displacement, we will have antinode at the end. Antinode at the end. But if sometimes if the diagram is given on one hand side, on the left hand side, it is given in terms of displacement. On the right hand side, it is given in terms of pressure. If this was displacement ka diagram and this was pressure ka diagram, then the correct answer would have been this. Do we understand this? Please remember this, bacha, and do not forget this ever, because this is going to be crucial for your understanding. Let me now take you to the next question. And the next question is, which one? Okay, this one. Question number 13 is what I have found for you. Can I have the answer for this one? In closed pipes, what are the position of antinodes? In closed pipes, where are the antinodes located? You know this. You just need to tell me what is the answer. Question number 13 from your sheet. Where are the antinodes located? In closed pipes. I might also show you that answer from the sheet. They've already covered it, bacha. In closed pipe, where are the antinodes? You can see the diagram here. And you can tell me where are the antinodes located. Where are the antinodes located, bacha? And the answer is, they are located at lambda by 4. Then after that, it will be lambda by 2 ahead. So lambda by 4 plus lambda by 2 becomes 3 lambda by 4, then 5 lambda by 4, then 7 lambda by 4, and so on. Do we understand this? Yes or no? No or yes? Well done, bacha. Now let us see, can I have the answer for this one, bacha? This one, this is question number 14. I hope you can see it. No, you can't see it, so I'll have to do some adjustments, and probably you would be able to see it now. What are the modes of vibration? What are the modes of vibration in a closed pipe? What are the modes of vibration in a closed pipe? Remember, they are not talking about displacement and pressure both. They are only talking about pressure. Closed pipes. Which is the correct diagram for a closed pipe? I think they have drawn the diagram wrongly. So let me take this question out because all the diagrams are drawn wrongly. So I will just not do that. The question is wrong. So I'll just move on to the next one, and the next one is here. Question number 24. Close pipe, length L, the fundamental tone. How much frequency is there of the fundamental tone, and which harmonics are present? Remember, we are talking about a closed pipe. Can I have your answers, please? In closed pipe, which harmonics are present, and what is the frequency of the first harmonic? Can I have your answers, please? And the answer is definitely C, 3. The first frequency, the first harmonic frequency is V by 4L, and only odd harmonics are present. Do we understand this? Yes or no? No or yes? Yes or no? No or yes? Well then, that brings us to an end of today's class. What we have done in today's class is that we have seen the reflection of sound waves. We have seen when the sound waves are getting reflected from a closed end, or when they are getting reflected from a denser medium, they will undergo a phase difference of pi. When they are getting reflected from a free end, they will not undergo any phase change. When two waves traveling in the same direction, having same frequencies and nearly same amplitude, whether they are sound waves or light waves, that is the last time we are hearing this, they superimpose. At some point we have constructive interference, at some points we have destructive interference. Do we remember this? Yes or no? For constructive interference, we have phase difference of 2n pi and a path difference of n lambda. For destructive interference, it is 2n minus 1 pi and 2n minus 1 lambda by 2. We have also seen what happens when two waves of same frequency and same amplitude, they are moving in opposite direction. When they superimpose, we have stationary waves. Remember, in stationary waves, we have talked a lot about stationary waves. Energy does not get transferred. They are restricted between 2 points. At some points, the amplitude is maximum. Those are known as antinodes. At some point, the amplitudes are minimum. Those points are known as nodes. We have also seen the vibration of air column in two types of pipe, closed pipe and open pipe. Whatever be the type of pipe, at the open end you will have antinode of displacement, and at the close end we will have node for displacement. Distance between two antinodes or the distance between two nodes is lambda by 2. Distance between one antinode and one node is always equal to lambda by 4. We have solved questions based on this. Where is the antinode? Where is the node? Where are the locations? I hope you are confident of solving any problem now. Can I have some raised hand that we understand this? Well then, in the next class, bacha, that is tomorrow, what we will do is we will go ahead and finish the remaining parts of the chapter, which would be dealing with beats. We have not dealt with beats, so we'll be dealing with beats, and we'll be doing the remaining portion in the class tomorrow. Take care, and I'll see you in the next class tomorrow. If you have any doubts, you can always come up to me. Take care.
Sir, good morning. Hello.